You know, I was walking through our office building this morning, one of those massive glass and steel places, and I had this sudden realization. It's kind of eerie. You
Right.
have thousands of people here. Everyone is on a video call, streaming 4K training videos, downloading massive data sets, and the internet just works. It
Yeah.
feels solid, like a utility, like water coming out of a tap.
It's designed to feel that way. That is the user experience we strive for.
Right, but think about the physical reality for a second. We've seen the server rooms, it's miles of copper cabling, thousands of plastic connectors, power supplies running hot, cooling fans vibrating 24/7.
Oh, yeah.
Physically, it is a chaotic mess of things that are just waiting to break. Statistically, something in that building should be failing right now.
Oh, statistically, something is failing right now. A router just blew a capacitor.
Yeah.
Or a cleaning crew bumped a power strip.
Exactly, but my Spotify stream didn't skip a beat. And that is what we are digging into today. We are looking at a stack of network architectural diagrams and protocol specifications that explain exactly how network engineers pull off this magic trick.
And spoiler alert, it's not magic. It's actually a very elaborate, high-speed deception.
Pure deception, I love it. We are doing a deep dive into first hop redundancy protocols, or FHRP,
Yep.
but specifically, we are going to tear apart the heavy hitter in the Cisco world, HSRP, the hot standby router protocol.
This is a classic topic, but it's essential. It's fundamentally about how we trick your computer, and by extension you, into staying connected when the physical infrastructure is actually crumbling.
The illusion of continuity. That's our mission today. We're going to figure out how networks cheat death. So let's unpack this. To appreciate the solution, I feel like we have to look at how surprisingly dumb our computers actually are when it comes to networking.
Dumb might be harsh, but they're certainly creatures of habit. They don't like improvisation.
Okay, let's set the scene. I'm a PC. I'm sitting at my desk. I want to send an email to a server in London. To get out of my local office network, I need to go through a door, right?
Correct. In networking terms, we call it the default gateway. Think of your PC as a person locked in a room. To talk to anyone outside, like Google, Netflix, or that server in London, it is to walk through a specific door.
And usually the IT team configures that door with a specific address, like 10.1.10.0.1.
Exactly. And here is the blind spot that the documentation highlights. Your PC is incredibly loyal to that address.
Okay.
It knows that one door.
Yeah.
It loves that door. It sends every single packet to 10.1.0.1. It doesn't look around the room for other options.
So here's the failure scenario. What happens if the physical router that owns 10.1.0.1 just, I don't know, catches fire?
Then you're stuck in the room. The PC doesn't have the intelligence to say, oh, door number 1 is blocked by a burning pile of electronics. Let me try the window.
No.
It just stands there, banging its head against the wall, screaming data at a dead IP address.
Even if there is a backup router, let's say $1 million piece of hardware sitting right next to it.
Even if it's plugged in, humming, and connected to the finest fiber optic lines money can buy, if your PC isn't explicitly told to use it, it won't. It doesn't know it exists.
That feels like such a massive design flaw in the way end-user devices work.
It's a limitation of the standard TCP/IP configuration on end devices. Simplicity is usually good, but here it creates a single point of failure. And that leads us to a key concept from the source material.
Which is?
Physical redundancy does not equal logical redundancy.
I highlighted that too. It basically means just buying 2 of everything doesn't save you.
Exactly. You can have 2 routers, 2 power supplies, 2 internet providers. That's physical redundancy.
Right.
But if your software, the logic doesn't know how to seamlessly switch between them without the user getting involved, you don't actually have redundancy. You just have expensive spare parts sitting on a rack doing nothing.
So we have the hardware, but we're missing the brain. Enter the solution. The diagrams here introduce the concept of a virtual router.
This is the core mechanics of FHRP. Since we can't easily teach every single PC in a 50-story building to look for a backup router if the first one dies, we change the environment instead.
Oh.
We stop using the physical IP addresses of the routers as the gateway.
So instead of pointing my PC at router A, the physical box, or router B, the backup box, I point it at a ghost.
Effectively, yes. We create a virtual router. It's not a physical box you can touch. It doesn't have a serial number sticker. It's a shared identity that sits between the physical routers and your PC.
Okay, so does this ghost have an address?
It does. The group of physical routers agrees to share a single virtual IP and a single virtual MSC address. You configure your PC to use the virtual IP as its gateway.
So going back to the room analogy, I'm not looking for door A or door B anymore.
No. You're looking for the magic door. And the
Yeah.
beauty is transparency. Your PC sends data to this virtual router. Behind the scenes, the physical routers, let's say router A and router B, are passing a baton. One of them is the active router, doing the actual work of forwarding packets. The other is standby, just watching.
But my PC has no clue this handoff is happening.
None. To your PC, the gateway is always there. It never changes. If the active router explodes, the standby router steps in, picks up the baton, and adopts that virtual IP.
So the face remains the same, even if the person wearing the mask has changed.
Exactly.
It's like a mascot at a theme park. The kid taking the photo thinks it's Mickey Mouse. They don't know, and honestly don't care, that it's a different guy inside the suit than it was yesterday.
That is a surprisingly accurate technical analogy. The Mickey Mouse suit is the virtual IP. The person sweating inside is the physical router. As long as the suit stays standing, the illusion holds.
Now, the source material mentions a few different flavors of this. We are focusing on HSRP, but that's not the only game in town, right?
No, it's not. HSRP, Hot Standby Router Protocol,
Yeah.
is the main character for our deep dive because it's the standard in Cisco environments, which, makes up a huge chunk of the corporate world.
Okay.
But it is Cisco proprietary.
Which means if I have a Cisco router and a Juniper router, they can't play this game together. They can't share the suit.
Exactly. They speak different languages. If you have a mixed vendor environment, which is common in really big networks, you'd use VRP.
VRP.
That stands for Virtual Router Redundancy Protocol.
Points for descriptive naming, I guess.
Yeah. Engineers aren't poets. VRP is the open industry standard. Functionally, it's almost identical to HSRP.
Yeah.
It has the same active standby model, the same virtual gateway concepts. It just works on everything.
Then I see one here that sounds a bit more ambitious. GLBP.
Ah, yes.
Okay.
Gateway Load Balancing Protocol. Also Cisco proprietary. This one addresses a big financial complaint about HSRP.
Which is?
Well, think about HSRP. You buy two expensive routers. One is working hard, the other is doing literally nothing.
It's just sitting there.
It's just burning electricity, acting as a standby. It's an expensive insurance policy.
Right. It's idle capital.
GLBP changes that. It allows multiple routers to forward traffic simultaneously load balancing while still providing backup for each other.
Oh, so you get double the bandwidth during normal times.
You do. It's more efficient, but it's also significantly more complex to troubleshoot.
And there was one more. IRDP.
We can gloss over that. The document's listed as legacy. It stands for ICMP Router Discovery Protocol. It's a relic from the 90s.
Got it.
In a modern switch network, you're choosing between HSRP, VRRP, or GLBP.
Okay, let's leave the relics in the museum and go back to our star, HSRP. I want to get into the nuts and bolts of how this mascot suit actually works, because the documents highlight something called the ARP trick. This seems to be the secret sauce.
This is where it gets really interesting for the technicians listening. This is the mechanism of the deception.
Set it up for us.
Okay, when your PC wants to send an email, it knows the IP address of the gateway, right?
Yeah.
The virtual IP. But, and this is networking 101, to actually send the data frame over the wire, it needs the MC address, the hardware address of the network card.
Right. The IP gets you to the neighborhood. The MA gets you to the specific house.
Precisely. So your PC shouts out using a protocol called ARP, Address Resolution Protocol. It asks the whole network, who has this IP address?
Who's the gateway?
Normally, a router would reply, I do, and here's my unique burned-in hardware address. But in HSRP, the active router lies.
It lies.
It spoofs. It replies, I do. But instead of giving its own real MC address, it replies with a special virtual MC address.
The source actually gives us the specific code for this. It's not just random numbers.
No, it's very structured. For HSRP version 1, that address always starts with 00000.0007 and ends in XX.
00000000000C is the Cisco vendor ID. 07IC is the code that indicates this is HSRP.
Right.
And the last two digits, C01, that's the group ID in hex. It tells you which HSRP group you're talking to. Why is this specific deception so important? Why not just use the real MC address of the active router and update it later?
Because of the benefit listed in our source. Seamless continuity. Your PC caches that MS address. It writes it down in a little address book so it doesn't have to ask every time.
Oh, okay.
If we use the real hardware address and that router failed, your PC would still be trying to talk to the old hardware address.
It would be mailing letters to a house that burned down.
Exactly. By using a virtual MA, when the backup router steps up, it just adopts that same virtual MA. To your PC, the destination never changed. It doesn't have to update its address book. It just keeps sending packets.
It's the perfect crime. The victim, my PC never knows the switch happened, but this brings up a question of hierarchy.
Yeah.
If we have two routers, say router A and router B, and they both want to be the one wearing the mascot suit, how do they decide who gets to be king?
That's the election. HSRP is basically a democracy, but it's a weighted democracy.
Go on.
The routers talk to each other and compare resumes. The most important line on that resume is a priority.
It's a score.
Exactly. The default score or priority is 100. The range goes from 0 to 255. The router with the highest priority becomes the active router.
So if I buy a massive, powerful router, let's call it the Beast, and a tiny, cheap backup router, I should set the Beast to, say, 150.
Ideally, yes.
Yeah.
That is the best practice. You want to manually configure the priority to ensure the most capable hardware is doing the heavy lifting. You don't want the cheap backup router handling your entire office's traffic unless it absolutely has to.
But what happens if I'm lazy? What if I pull them both out of the box, plug them in, and leave them at the default 100? They're tied.
In the event of a tie, HSRP has a tiebreaker. It looks at the IP address. The router with the numerically highest IPv4 address on the interface wins.
Wait, really? So if router A is 10.1.10 narrow 0.2 and router B is 10.1.1.3, router B wins just because 3 is bigger than 2.
Correct. It's totally arbitrary.
That sounds remarkably unprofessional for a protocol that runs the internet.
It's just a deterministic way to break a deadlock. But that's why the source emphasizes not relying on chance. You don't want your backup router becoming the primary just because it happened to get a slightly higher IP address. You should control the election with priority.
Okay, so let's play out a scenario. We have our king. Router A is active, priority 150. Router B is standby, priority 100. Everything is great. But then router A crashes.
Right. Router B notices the silence, steps up, and becomes active. It's handling all the traffic now.
But then, and here's the twist, router A reboots. It comes back online. It's healthy again. It still has priority 150. Does it walk back in and say, I'm in charge?
This is a crucial nuance that catches a lot of junior engineers off guard. By default, no.
Really? Even though it has a higher priority?
Even though it's the better router,
Yeah.
HSRP prioritizes stability over hierarchy. If router B is doing a fine job, the network doesn't want to cause another brief disruption by swapping back, just for the sake of the score.
So it just sits there.
So router A will come back online and sit in the standby role.
That seems inefficient, though. If router A is the big, expensive machine, I want it doing the work. I don't want it sitting on the bench while the scrub plays the game.
Exactly. And that is why we have the concept of preemption. This is the Game of Thrones part of the protocol. There is a specific command called standby preempt.
Preempt. Sounds aggressive.
It is. If you enable this command on the routers, it changes the rules. It tells the router, if you have a higher priority than the current active router, do not wait. Overthrow them immediately.
So with standby preempt, router A comes back online, sees it has a 150 score against router B's 100, and kicks router B out.
Immediately.
Yeah.
It reclaims the active role. This logic is critical for ensuring traffic returns to your primary hardware after a recovery. Without it, you might have your network running on backup hardware for weeks until someone notices.
Or until the backup hardware melts because it wasn't designed to run full-time at peak load.
Precisely.
Okay, we've talked about elections and coups, but let's talk about the communication itself. How does the standby router know if the active router is dead or just thinking?
It's all about the heartbeat. The routers exchange multicast hello packets.
Like a pulse.
Exactly. The source details the specific timings here, and they are vital for understanding how fast a failover actually happens. The hello timer, the heartbeat, happens every 3 seconds by default.
So every 3 seconds, the active router says, I'm here, I'm here, I'm here.
Correct. And the standby router is listening. Now, there's a second timer called the hold timer. This is set to 10 seconds.
Why 10?
It's roughly 3 times the hello timer plus a buffer. Think of this as the time of death. If the standby router hears nothing for 10 seconds.
It assumes the active router has failed. It declares the king dead and initiates the failover.
That's the one.
That seems pretty reasonable, 10 seconds. But can we tweak that? If I'm a high-frequency trader or I'm running a hospital network, 10 seconds is an eternity.
You can tweak it. You can knock those timers down to milliseconds if you want. But the source includes a big optimization warning.
What's the risk? Faster is better, right?
Not always. This is the classic engineering trade-off. If you make it too sensitive, say you set the hold timer to 200 milliseconds, you risk CPU instability.
How so?
First, the router is spending all its CPU cycles screaming, I'm here, instead of routing traffic. Second, and more importantly, false positives. If the network gets a little busy and a whole packet hello packet gets delayed by just a fraction of a second.
The backup thinks the primary died.
Exactly, it tries to take over.
Okay.
Then the packet arrives, and the primary fights back. You get a flapping link where the routers keep fighting for control, swapping back and forth rapidly. That is much, much worse than a 10-second outage.
Right, nobody wants a flapping router. Stability is key. Now, briefly, before we wrap up, let's look at the life cycle. The documents mention that a router doesn't just turn on and immediately become active. It goes through steps.
It's progression. When an HSRP router boots up, it starts at initial. Then it goes to learn, where it's waiting to hear if anyone else is already out there and what the virtual IP is.
Okay.
Then listen, it knows the virtual IP and it's just listening for hellos.
Then speak.
Yes, speak. This is the teenage phase. It starts sending its own hello packets and participating in the election. From there, it moves to standby waiting in the wings, and finally, if it wins, active.
It helps to see that progression when you're troubleshooting. If you see a router stuck in speak, you know it's having trouble negotiating.
Exactly. And if you're the engineer running in with your hair on fire because the internet is down, there is one magic command you need to know to check all this.
Hit me.
Show standby.
Simple.
That command is your dashboard. It tells you the state, active or standby, the virtual IP, the virtual MIC, and whether preemption is enabled. It's the first thing you type.
So let's zoom out. We've gone through the smoke, the mirrors, the virtual identities, the elections, and the timers. It's a massive amount of engineering just to make two boxes act like one.
It is. But HSRP creates a logical abstraction. It separates the messiness of physical hardware, where things break, cables rot, and power fails, from the user expectation.
Which is that the internet is eternal.
Exactly. It bridges the gap between reality and expectation. In a modern switch network, without a protocol like HSRP, a single router reboot could isolate an entire office floor.
Wow.
It wouldn't matter if you had paid for a backup router. Without the protocol to manage the handoff, you're offline.
It's the difference between having a spare tire in your trunk and having a car that automatically changes its own tire while you're driving down the highway at 60 miles an hour.
That is the illusion of continuity.
I want to leave you with a thought, though. We talked about that hold timer being 10 seconds by default. That means in a standard setup, if a router blows up, there is a 10-second black hole. The internet just stops for 10 seconds before the backup kicks in.
It's a lifetime in the digital world.
Exactly. In a world of real-time gaming, Zoom calls, and high-frequency trading, is 10 seconds acceptable? Or is that 10 seconds of silence actually an eternity? What happens to your data in that gap?
That is the question every network architect has to answer when they set those timers. How much risk can you stomach for speed?
Thanks for diving in with us.
A pleasure.
We'll catch you on the next one.